Hello and welcome to my presentation on the paper Alkyne Metathesis Reactions of Rhenium-5 Carbine Complexes. So to begin, we'll start with an introduction to Rhenium-5 carbine complexes. So, alkyne metathesis reactions facilitated by high-valent D0 carbine complexes have been extensively studied and well documented. While those involving low-valency non-D0 complexes are notably rare, Rhenium-5 introduces its D2 state as a viable approach for enabling reversible cycloaddition reactions of alkyne carbines. The scarcity of metathesis or cycloaddition reactions involving non-D0 carbine complexes and alkynes may stem from the challenge non-D0 metal centers face, this being forming alkyne carbine complexes with the prerequisite parallel alignment of ligands. When comparing structures 6A and 6B, these two here, the crucial distinction lies in the orientation of the alkyne ligand, either perpendicular or parallel, which alters the electronic effect of the metal center. Despite the electronic preference for the 6A orientation, the 6B orientation is essential for facilitating the reactions. In a D2 fragment with structure 6 sigma, this one here, the T2G set d orbitals are non-degenerate. The dxy and dyz orbitals are energetically higher than the dxy orbital due to their interactions with the pi-type orbitals of the carbine ligand. In structure 6A, multiple stabilizing effects occur between the dxy and dyz orbitals and the pi star squared orbitals. Conversely, in 6B, a repulsive interaction arises between the filled dxy orbital and the filled pi1 orbital of the alkyne ligand. However, these challenges are surmountable, as demonstrated by the successfulness outcomes of the reactions. So the electronic effects are also between the different orientations are the main reason these low valence states are unfavorable and don't always work. Which is why Rhenium-5 can have these two D2 carbine complexes. The way we break through this is by using a different structure, the one here labeled 8, by layering the steric effects of small ligands trans to the carbine ligand and bulky ligands cis to the alkyne ligand as shown in 8. So, moving on to the reactions. So, the reactions. So, reaction 1 is a metathesis reaction involving the alkyne ethyl 3-trimethyl-silopropyolate and the complex 9. You can see the reaction going forward here. The alkyne reacts, takes the bromobenzene and puts it on instead of the ester, and then the ester becomes the new alkyne bond. Now, the initial reaction observed involves testing the proposed structure depicted as structure 8, which is down here, with the layered ligands arranged cis and trans to the metal. The reaction conditions employed were rather harsh, carried out in a nitrogen atmosphere and dissolved in toluene solvent at 110 degrees for 12 hours. Confirmation of the reaction was attained through phosphorus NMR spectroscopy with decoupled hydrogen. The peaks observed validated the formation of the new structure, along with the isolation of the product, complex 10, as a blue solid, and the extraction of the tetramethylsilane bromobenzene equivalent, which is this, through column chromatography. Among the notable interactions, there's the synthesis of compound 12 on this image, utilizing the diaryl acetylene and siloalkyl CH2-CH3 chains, which is creating compounds 12, 11, 13, and 12 also. There's an intriguing discovery which lies in the reaction involving the carbines. When complex 12, which is this one, is reacted with the original carbine from reaction 1, the 3-ethyl-3-trimethylsilate propyolate, it reverts back to complex 10, suggesting a degree of reversibility in these reactions and showing that they can be further studied without having to continuously make up new original material, since the yields amount are quite low in proportion to what's going in. The metathesis reactions present an intriguing aspect, as reported instances of well-defined non-D0 carbine complexes undergoing alkyne metathesis reactions are exceedingly rare, primarily limited to tungsten complexes, as there's only one that actually currently works. Furthermore, this transformation offers a pathway to produce Rhenium-5 carbine complexes that are not readily accessible through other means. So, some information on the Rhenium-5 complexes. The oxidation state is fairly obvious, with this being on Rhenium-5 and every complex containing a D2 Rhenium-5 at its core. The electron counting consists of 15 to 16, and this is where it gets a bit interesting. The complex proposes some issues and inconsistencies with the electron counting. Firstly, the chlorines, phosphorus, and actual metal itself all propose 2 electrons each, which equates to 12. Now, as per standard, the carbine bond should give 3 to this number, making the 15 half. However, having 15 makes it incredibly unstable and violently reactive. Now, this may be the goal, as these complexes are quite difficult to react and obviously have the barriers to get over to actually create the reactions themselves. However, it could also be likely that the carbine has a strange interaction with the metal center, in which, because a triple bond needs 6 electrons to exist, it still retains 1, allowing the bond to contribute 4 electrons, creating the 16 number. So some final results and analytics here. So there were 3 different types of NMR used, which was hydrogen, carbon, and phosphorus, with 2 of them being decoupled hydrogen. The reaction between complex 9 and 10, the reaction was successful, as well as all the other ones that were produced on the slides. Just that particular reaction had a 45% yield, as well as column chromatography with a silica gel based column was also used to identify the reacted solvent as a pale yellow oil diffracted from the solution, which was the tetramethylsilyl bromobenzene derivative we saw previously. Now, based on that image as well, with all the different reaction complexes, the yields for these reactions ranged from as low as 29% to the highest being 69%, showing that the reactions are possible with relatively high outcome yields. And the modeling image we saw, that was produced by X-ray crystallography of complex 10, showing the structure, the octahedral structure, as well as the bond angle and lengths. That was also performed to identify and characterize the complex to ensure it was the correct outcome, and to see what sort of properties the bonds and the metal complex would have on it itself. These are all done to ensure that more research would be done, and to see what sort of other reactions and possibilities could be done, as there is still a lot unknown about the low valency non-D0 complexes. Thank you very much for listening. I hope it was educational.